Our galaxy alone is home to at least 100 billion stars. And yet, we often think other stars resemble the one bathing the Earth in light and heat. But stars aren't all the same. They differ in brightness, temperature, size, color, and mass. Stars can be dimmer than the Earth, be just about the same size as our moon, shine a few million times brighter than the sun, and grow as big as Saturn's entire orbit. But what would such stars look like from our planet if the sun was suddenly replaced with them? Now get ready to find out the answers to this and more. Stars are born in clouds of gas and dust called nebulae. As gas molecules and dust particles come together, they collapse under their own gravity and heat up to form a protostar, the initial phase of a star's evolution. As a hot core forms and gathers material, it continues to heat up, and once it reaches about 15 million degrees Celsius, a star enters its main sequence phase and nuclear fusion begins. That's how a star will spend about 90% of its time. Scientists think that to sustain nuclear fusion, a star can be no smaller than 8.7% the diameter of our Sun, which is roughly 1.39 million kilometers. With a bit of calculations, these 8.7% translate into about 120,000 kilometers. But that's still a bit smaller than Jupiter, which is, like most stars, made of hydrogen and helium. So why isn't it a star? Jupiter just isn't massive and dense enough. It lacks internal pressure and temperature to sustain nuclear fusion. Generally, the more mass a star has, the shorter its lifespan. A star the size of our Sun will stick around for roughly 10 billion years, but one that's 10 times more massive than that would only live for about 20 million years. But what happens after that? Approximately 97% of stars will become white dwarfs, and just recently, scientists discovered a miniature white dwarf around 4,300 kilometers wide and 45,700 degrees Celsius in temperature. That's just a bit larger than our moon and is roughly the distance from Los Angeles to Washington, D.C. But don't be misled by the tiny size of this star. It has 35% more mass than our yellow dwarf sun. In fact, 1 teaspoon of matter from a white dwarf star would weigh as much as a 5.5-ton elephant on Earth. This makes it the smallest and yet the most massive white dwarf discovered so far. This white dwarf also makes a full 360-degree rotation in just 7 minutes, which is 200 times faster than our planet rotates. But could we survive living near a white dwarf? As our Sun will eventually become a red giant when all of its fuel is used up, it'll transform into a white dwarf. But let's say, for example, that planet Earth was placed in the habitable zone of a white dwarf. Generally, white dwarfs are bright enough to have habitable zones around them, but too dim to extend the habitable zone far enough to where we are now from our Sun. A habitable zone around a white dwarf begins at about 1/100th the distance that our planet is to the Sun, and that's quite dangerous because of the gravitational force. That gravitational force would tidally lock our planet. Although a tidally locked planet would look interesting because of the permanent night side and day side, the gravitational pull of a dead star will heat and flex Earth a lot. The closest planets, Mercury and Venus, will be, most probably, obliterated. But that's just the beginning. Over time, white dwarfs cool and emit less light, thus shifting their habitable zone closer and closer to a dead star. This means all the water on Earth would freeze, and with less light, we'd be bathed in high-energy radiation. If that happens, our planet would become more like Venus, with an atmosphere filled with carbon dioxide. Now, what about the stars that are bigger than white dwarfs, and how do we even measure the size of a star? It turns out that scientists can tell how big a star is by knowing its surface temperature and luminosity, which is the energy that a star emits. They've even come up with a special diagram that can predict the size of a star depending on the above-mentioned criteria. Although we think something's hot if it's orange or red, with stars, it works the other way round. The hottest stars out there have blue hues, while cooler stars appear to be red. And this representative of a very rare stellar class of stars is just an example of this rule. It's one of the hottest stars ever discovered. With a radius half that of our Sun, The surface temperature of WR102 is 35 times hotter, and it's got a blue color. But that's still quite smaller than our Sun, and the universe has a lot more stars that are both bigger and more interesting. HD 140283, or Methuselah, is a star that's 1.7 times larger than our Sun. It also has a mass roughly 0.8 solar masses and is about 5 times more luminous than our star. Methuselah is one of the oldest yellow subgiants that we've ever discovered. In fact, it's so ancient that scientists' initial calculations showed it was 16 billion years old, which is odd if the universe is only 13.8 billion years old. But even according to recently revised estimates, this star still seems to have been born shortly after the universe itself. The next star is just a toddler compared to the previous old-timer, but it has some other features that make it stand out. R136A1 is about 30 times our Sun's radius, but it's one of the brightest stars out there. If our Sun was replaced by this star, you probably wouldn't be able to go out without high-quality sunglasses on a sunny day. Breaking the earlier accepted limit of 150 solar masses, this star is a whopping 265 times as massive as our Sun. This number is so huge that it potentially points to the most massive star out there that makes all other known stars pale in comparison. Sadly for this star, due to its extreme mass, temperature, and luminosity, it's doomed to a short life. It's believed to be 1 million years old, and it only has about the same amount of time left before it goes hypernova. R136A1 is a real heavyweight, but its size is still quite tiny compared to a bluish-white supergiant called Alpha Cygni. This monster is roughly 200 times the size and at least 50,000 times more luminous than our Sun. However, Alpha Cygni is just about 19 times as massive as our star, and now imagine how this giant would shine seen from the Earth if it were our Sun. Now let's go to the red supergiants. Meet Antares, a star that's about 680 times the Sun's radius, which is more than 3 times the distance from Earth to the Sun. What this means is that if one day our star was replaced by Antares, our planet and even Mars would have been swallowed by it. But if it was a bit further, the red supergiant would look like a big burning ball of hot plasma, about 1100 times brighter than the Sun. But even a star of this size is nothing compared to the largest one we've been able to detect. Stephenson 218 currently holds the title of the biggest star and is the most luminous red supergiant in the entire universe. The star's radius is nearly 2,150 times the Sun's radius, which is a number that can hardly be grasped by our brains. 3 billion kilometers. Our Sun has a volume of about 1.3 million Earths. Now consider this. Stephenson 218 can fit inside a whopping 10 billion suns. To say it's a huge star is an understatement. Nevertheless, even that is not the limit to how big a star can grow. A hypothetical quasi-star, known as a black hole star, could be much, much larger. Scientists believe these existed at the dawn of the universe, and their size could have been approximately 10 billion kilometers. To give you a bit of perspective, it took nearly 10 years for the New Horizons probe to get close to Pluto, and it would need 5 more years to get out of the quasi-star if it was trapped in one. If one still existed, a quasi-star would produce as much light as a tiny galaxy. That would be a breathtaking phenomenon to contemplate. There are many stars that are much more intriguing than our boring, average-sized Sun is. And while it would be a lot more fun to look at those fascinating stars from the Earth, life on our planet is too sensitive for such entertainment. Even the slightest changes in the temperature, radiation, and light could mean an absolute disaster for us. May other stars be 1 billion times brighter, hotter, or bigger, we're still 1 billion times luckier, because we can admire these huge, bright monsters through telescopes and live side by side with probably the most favorable star for life.